Um, okay, so now we're ready to introduce double integrals. So if you remember back to Calc 1, when you calculate the definite integral of a function f of x, the result of the calculation is just a number. And geometrically, what this number represents is some kind of net area, either positive or negative, depending on whether the function is above the x-axis or below the x-axis. And okay, so the number represents some kind of area for the function, right? So if we now take a look at a function of two variables, the graph now looks like a surface within three-dimensional space, and so we want a double integral calculated over a rectangular region like this to represent some kind of volume. Again, here the function is positive, so the volume will be positive, right? So you can see these dotted lines carving out this solid region here between the graph and above the rectangular domain. So again, we want to figure out how to calculate such a volume. Okay, so to start off, we're going to keep things simple, and the domain of integration is going to be a rectangle where x varies between a and b, and then y varies between c and d. So a double integral is written like this, right? So the domain of integration, here being described as r, is written here underneath the double integral symbol. My function now is a function of two variables, and here we write dA because now when we sort of partition these regions, they represent area instead of just a single variable. Okay, so this is how we represent a double integral, but how is it actually calculated, right? So so here, because both x and y is varying, the double integral is going to involve both the variables x and y, and the way it's calculated is so you have to decide which variable to integrate first. However, if it's written like this, we integrate with respect to y first, and the inner integral written here is a partial integral, right? So this integral is kind of like this partial integral here with respect to y, right? So you notice how when you have a partial integral with respect to y, the result could be a function that only contains x, and so in this type of calculation, this partial integral on the inside you calculate first. It results in something that only contains x, and then you calculate the outer integral, which is just a normal integral with respect to x. And you can also set up the integral the other way, where the inside integral is a partial integral with respect to x. The result of that is something containing the variable y, and then you calculate the outer integral, which is just a regular integral with respect to y. So you can set it up either way, and through this theorem called Fubini's theorem, as long as your function is nice enough, which in this course we'll stick with pretty well behaved functions. So in this case, when you integrate over a rectangular region, it doesn't really matter the order of integration you do, right? So whether it's y first and then x, or x and then y. However, depending on the way you set it up, you have to make sure that the limits of integration match up with the corresponding variable, right? So Here the inner integral is with respect to y, so the limits of integration are c and d. The outer integration with respect to x, so the limits here are a and b. And then here it's just switched around. So again, typically in these double integrals, you integrate one variable at a time, and you calculate the inner integral first as a partial integral, and then once that's completed, then you calculate the outer integral, which is an ordinary integral. So that's the basic idea. Next page we'll look at an example of such a calculation.